Yes. Oh, hello everyone. So in this session, we will move on to coordination compounds, coordination chemistry. So this is again another important chapter, right? So what all we study here is the properties of coordination compounds, right? And the isomerism and the theories, different theories of coordination compounds. These are the three important things. In that, the oftenly asked questions come from the IUPAC naming of coordination compounds and isomerism questions can be asked, or based on the theories, few questions can be asked. So yeah, so we have talked about such kind of complexes and coordination. This kind of coordination compounds are formed by transition elements. This transition element Fe is capable of doing this kind of complexes or coordination compounds. So in coordination compounds, what we see is something is written in the square bracket entity and something lies outside of it. And it can be a cation or anion. In this case, it is a cation, potassium ion. 4 such K plus ion is there. They are called counter ions. Let us know the terms from this. This is called Fe, which is in the square bracket. That is called central metal ion. It is a central metal ion. The one which is along with the central metal ion is called ligand. Ligand is the one which is capable of donating a pair of electrons, right? So, and the six, how many numbers of ligands are there? That is called coordination number. That is called coordination number of this particular compound. So this total one which is written in the square bracket entity is called coordination sphere. It is coordination sphere. And these are counter ions. Okay, these are called counter ions. Just a minute, I'm searching for the pens. I will get the pens. Right. Okay. Now suppose if I take CuS, okay, Cu H2O 4 times and SO4. Now in this coordination compound, copper is the central atom and H2O is the ligand and 4 is the coordination number and counter ion is an ion, that is sulfate ion, right? Now sulfate ion is having 2 charge, SO4 2 minus, we know that. Therefore the complex should get 2 plus charge so that the total compound is neutral, right? Now copper and H2O 4 times. H2O is a neutral ligand. H2O is a neutral ligand. We know that H2O is a neutral ligand. Therefore, the charge on the complex should be the charge of copper. So copper exists here in the +2 oxidation state. Copper is in +2 oxidation state. So this is required while naming the coordination compounds, right? So this is about the different terms in the coordination compounds. Now, coordination compound consisting of a complex ion. Okay, all these things I have told you once again. This complex ion here is the one which is in the square bracket entity and carries +2 charge. And these are the 2Cl minus are the counter ions. And this is consisting of two different kinds of ligands. One is chloride ligand, chloride. This is not neutral. So Cl minus is the ligand in case of this. 5 ammonia, ammonia is a neutral ligand and Cl is having negative charge. So this is negatively charged species acting as a ligand. Now it is heteroleptic complexes. If there are more than one type of ligand, heteroleptic complex. If there is only one kind of ligand, then it is homoleptic complex, right? Now usually these ligands will, with the central atom, they form a definite geometry. This geometry is called coordination polyhedra. You can able to see here, there is a central atom and there are 6 ligands forming or arranging themselves in the geometry octahedral. This is called octahedral, right? Octahedral geometry. So these are octahedral geometry. These are in the solid Cl3. This is Cl minus ions are separated if it is in solution, right? Counter ions get separated, but the one which is in the square bracket entity, it is not ionizable. That is not ionizable. This is not answering any presence for the chemical test. Now there can be a square planar complex. You can see a square planar complex, right? PTNH3 4 times. It is a platinum complex. Platinum complex. These are all ammonia, right? So this is the way the transition elements are present. So complex ion species where transition metal ion is surrounded by certain number of ligands. A complex ion is one in which to which the there are certain number of ligands are surrounding. So transition metal in this way is called Lewis acid and ligands are Lewis bases. As we have discussed there, the Lewis bases are the one which is capable of giving a pair of electron, right? Bronsted and Lorry's theory, then Lewis theory we have come across. Lewis theory is the one which accepts a pair of electron is acid. So central metal atom, probably it is a transition metal ion or a metal atom. This receives a pair of electron, therefore it is an acid. And ligands are Lewis bases, right? Okay. Okay. Now ligands. Okay, ligand. Okay, this is the complex ion. The complex ion, there can be definite coordination polyhedra. If there are 2 ligands, then it could be linear. If there are 4, then the geometry can be square planar or tetrahedral. It can be square planar or tetrahedral, right? Copper CuCN4 3 minus is tetrahedral, whereas NiCN4 2 minus is square planar. This is an example for that. So let us know why it is forming tetrahedral and square planar complexes, even though there are 4 ligands, right? So let us know about the theories. From the theories, we'll understand more about it. And if there are 6 number of ligands, then octahedral. Okay, these are the only types of geometries that we find in the coordination compounds. Linear, then AgNH twice, AgNH3 twice plus intolerance reagent, what we have written. Linear, if the 2 ligands are there. If the 4 are there, then it can be square planar or tetrahedral. If the 8 are there, then it is octahedral. Now, what are ligands? Ligands are the maybe negatively charged or neutral species. Neutral species, they have the ability to give a pair of electrons. They have the ability to give a pair of electrons, right? So if if a ligand can give one pair of electron, then it is a monodentate ligand. It is named as monodentate ligand, right? And if a ligand can two, then it is called bidentate ligand, right? NH3 is a monodentate ligand because nitrogen contains a pair of electron to donate. It is a monodentate ligand. Okay. And didentate ligand. Okay. CH2NH2. CH2NH2. This is ethylene diamine. There are two NH group. Both nitrogen is capable of binding the central atom. So it is a didentate ligand. So two ligating atoms in one particular molecule, two ligating atoms, both getting connected to the central atom, they are didentate ligands. There can be polydentate ligands also. EDTA is a polydentate ligand or a hexadentate ligand. It can give a 6 pairs of electron. Okay. Now let us look into the structure of them, right? Unidentate ligand. Probably you have to remember this. H2O is a unidentate ligand. Even though oxygen contains two lone pairs, it is capable of giving only one pair, right? So therefore it is unidentate or monodentate. Both are same. NH3, fluoride ion. These are negatively charged. Fluoride ion, chloride ion, negatively charged. Cyanide ion. Okay, cyanide ion, thiocyanate ion, SCN. These are monodentate ligand, unidentate ligands. Hydroxide ion or nitrite ion. Nitrite ion. These are all the negatively charged species acting as a monodentate ligands. Bidentate ligand, as I told you, CH2, CH2, NH2, NH2. That is ethylene diamine, abbreviated as ENE. ENE. Oxalate ion, COO, oxalate ion. What is oxalic acid? COOH, COOH, right? Okay. If this hydrogen goes away, giving negative charge, COO minus, COO minus, this is a didentate ligand. Both this oxygen can capable of binding the central atom. Polydentate ligand, you can see this. This is EDTA. Okay. Ethylene diamine tetraacetate, CH3COO, tetraacetate. CH2COO, this is 4 are there, tetraacetate, right? So this is the ligating atoms are 1, 2, 3, 4, 5, 6. Therefore, it is hexadentate ligand. Okay. 2 oxygen and here 2 oxygen, here totally 4 oxygen and 2 nitrogen. 6 pairs of electrons it can get at a time. Whenever such kind of ligand is present, it can bind. It is called chelating ligand. The ligand which is can able to give one particular compound, if it able to give many number of electrons, or it can bind the central atom by using many number of electrons, then it is a chelating ligand. Chelating ligand forms a ring-like structure, right? So that it will hold by the different hands, just like octopus, right? Octopus is having more tentacles and it can catch. In the same way, so if it is a chelating ligand, the stability of such complexes increases. Stability of that complex increases, right? So EDTA is such a kind of chelating ligand, right? So these two are here. These two are symmetrical didentate ligands. Symmetrical. So you can see they are symmetrical. CH2NH2, CH2NH2, right? COO, symmetrical didentate ligands. Okay. So in this way, you have to have more and more information about the ligands. Now, how to write the formula of the compound, and how to, if the formula is given, how to name them. Let us look into both of that. So always when the formula, cation is to be written first, then anion. For the formula, writing of the formula, cation is to be named first and then anion. total charges must be balanced to 0. Coordination compound, totally it should balance to 0. Complex ion should be written in bracket. This is the way of writing, right? K2, CO, NH3 twice, Cl4. It is a heterolytic complex. NH3, 0, because neutral ligand. Chloride, -1. Okay. Cobalt here is +3. +3, oxidation state. +3 -1 is +2. Okay, so sorry, -1 into 4 is -4 is there. Okay, -4, it should be -1 into 4, totally -4, +3. Okay, it should be, cobalt should be in +4, +2 oxidation state. So that total charge is -2. It should be in +2 oxidation state. So that -4 +2 is -2. The charge on the complex is -2. The counter ion +1 is, K +1 is 2. Therefore, totally it is 0. In this way, we have to see that the complex as a total is having 0 charge. It should not be a charged compound, right? It can be an ion, right? If it is to be ion, it can be ion. The total charges written should be tally with the charge on the ion. It should tally there. Now, names of the coordination compounds: cation, then anion, again ligands. Ligands are to be arranged alphabetical. It should be written in alphabetical. Okay. And anionic ligands are, instead of IDE, IDO is being used. Prefix indicates the number of each. How many ligands are there? That should be the prefix of that. Oxidation state of the metal ion is to be written in parenthesis, bracket. If a complex ion is an anion, then metal should end with 8. Metal should end with 8. So these are the consolidated rules for writing or naming a coordination compound. Okay. Now, specific cases. Suppose if the ligands are neutral, water, ammonia, carbon monoxide, nitrogen monoxide, then they are named as aqua, amine, carbonyl, nitrosyl. This is the way we have to spell while naming. Fluorine, fluoro, okay, fluorido, chlorido. It should be fluorido, chlorido, bromido, iodido, like that. Now, names of some metal ions in the complex anions. If a complex square bracket entity carry negative charge, then the central metal atom present here should be pronounced like this, or it should be named like this. If it is Fe is present there, it will be named as ferrate. If copper is present, cuprate. Lead, plumbate. Silver, argentate. Gold, aurate. Tin, stannate. Okay, these are the names to be written. Okay, we'll take the specific examples. Yes. Now, how to name this? First, cation. Cation is potassium, right? Then anion. All inorganic salts. First, we have to name cation. This is potassium. Then, when we come to the complex ion, it is the ligand first, that too in alphabetical order. Ammonia. Okay. Ammonia is amine. Okay. So, prefix, number of that kind of ligand. This is diamine. Ammonia is spelled as amine. Diamine. Tetrachlorido. 4 chloride ions, chlorido. This is the way we have to pronounce. Cobaltate 2. Why cobaltate? This is cobalt, but this whole complex carry negative charge, -2 charge. Since this is negative charge, this cobalt, this is not simply cobalt, it is cobaltate. So, their suffix is 8. As we say, for the sodium and chlorine, one which is made up of sodium and chlorine, we say that sodium chloride, right? Potassium bromide, IDE is the suffix. In the same way, here we take the metal atom at the end. of the end of the naming the complex entity, then it should end with 8, followed by the oxidation state in parenthesis, bracket. Now, coming to this, so here this is complex ion is a cation, counter ion is an anion. So we should always cation first. When it is complex ion, among that tetraamine, so always ligands first, alphabetical order, then metal atom. Metal atom or ion. Tetraamine, dichlorido, cobalt 3 chloride, cobalt 3 chloride. So oxidation number is 3, cobalt 3 chloride. You can write the oxidation number by calculating that the total charge carried by the complex ion is 0. Now, some more examples. You take some more examples so that you will be comfortable. This is cation first. Tetraamine, diaqua. If the water is there, we have to say aqua, diaqua, cobalt 3. All should come in without any gap. Without any gap, you should write. This is the right way. Don't give gap. Tetra and amine, don't separate them. Cobalt 3 and chloride. Don't say that this is trichloride. Okay, for the counter ions, you should not give the prefix. Okay. For example, I tell you, how do you name this ionic compound? It is not barium dichloride. It is barium chloride, right? We want to give prefix. Okay, only for the ligands, prefix is needed. Number, prefix is needed. Diaqua, it is needed, but not for the counter ions. Okay, counter ions are being given based on the fact that the whole total, it should be neutral. So to make neutrality, this contains +3 charge, therefore there is -1 charge should be 3. Based on that, the 3 is written. Right. Now this, there is ene, abbreviation is being given. Whenever abbreviation is given, ene or ox, we can use tris instead of tri, tris. Bis, tris. Bis for 2, tris for 3. More than 3 will not be there. Ethane 1,2-diamine. Ene is nothing but ethane 1,2-diamine. This is the one. Ethane 1,2-diamine. This is ethane 1,2-diamine. Ethane 1,2-diamine. This is abbreviated as ene. Chromium 3 chloride. Chromium 3 chloride. Okay. Now try yourself. Take a paper. This is,
Sir, pentaamine
this is to be
chlorido.
named first. Pentaamine chlorido. If it is only one is there, you need not say monochlorido. It is can be chlorido. Pentaamine chlorido. Cobalt. In parenthesis, its oxidation state, chloride. Now let us find out the oxidation state. Right? NH3 is neutral and chlorine is -1. Okay. So let us call it as X. Okay. So if chlorine is -1, we know always whether it is a ligand or a counter ion, it is -1. -1 into 2 is -2. So total charge due to counter ion is anion is -2. Therefore, this must be 2 plus. The square bracket should have 2 plus. Therefore, the complex is CO NH3 5 times Cl. This complex should have 2 plus as the charge. Now this is 0, this is -1. X plus 0 minus 1 is equal to 2 plus. Now find out the X. This is +3. Correct? So it should be written in parenthesis cobalt 3 chloride. Okay, all these calculation to be done. to find out the oxidation number. Okay. So even it is a small change, small mistake, total marks will be cut. Remember that IUPAC name should be 100% correct. Right. So pentamine chlorido cobalt 3 chloride. What about this? This dichlorido bis ethane 1,2-diamine platinum. Okay. Platinum 4 nitrate. Platinum 4 nitrate. Okay. Look at this. Pentamine chlorido cobalt 3 chloride. Dichlorido bis ethane 1,2-diamine, that is for ene, platinum 4 nitrate. So NO3 twice. NO3 is -1. So twice is there means -2 charge. This must be 2 plus charge. Ene is a neutral ligand. Chloride is -1. -1 into 2 is -2. So it must be +4. +4 -2 is equal to +2. All these things are to be done. Now, try yourself. This is oxalate ion, C2O4. C2O4 is oxalate. Trioxalato. Okay, potassium trioxalato ferrate. Trioxalato ferrate. Why ferrate? Because it is negative charge. Counter ion is cation. So if it is anion, then we should get that ferrate. Here potassium tetrachlorido palladate. Palladate 4. Palladate 2. Palladate 2. Potassium trioxalato ferrate 3. Ferrate 3. Potassium tetrachlorido palladate, because it is not simply palladium, palladate, because anion. Palladate 2. Since it is 2 plus 2 and is -1 into 4 is -4. So total charge is -2. Therefore, +1 is 2. Correct. Palladate 2. There are many questions that you can solve like this. I'll give the answer. You can just check. So no much time is available and you must have practiced it also. Diamine. This is diamine. Chlorido. This is CH3NH2. Therefore, methylamine. Platinum 2 chloride. Platinum 2, when it ends, chlorine is chloride, not chlorido. Here it is chloride. When it is inside, then it is chlorido. Okay. Coming to this is hexaamine. Cobalt 3 sulfate. SO4 2- is sulfate. Okay. So whenever it is like this, the ions that you may split and understand. CO, NH3, 6 times 2. 2 is there. Okay. Therefore, the number of ions of this kind will be 2. Okay. 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 This 3 plus sulfate ion, that is 3. There are 2 such kind of ions and 3 sulfate ions. This ions 3 charge, 3 into 2 plus 6 charge, 3 into -2 -6 charge, so that it is neutral. Okay. So these things, how these 2 and 3 have come, because to make neutrality. Okay. Okay, I will give the answers. Pentaamine, pentaamine. If it is written ONO instead of NO2, if it is written ONO, then it is nitrito O. Nitrito O. See, NO2 is having NO2 is having two ligating atoms. It can bind with nitrogen or it can bind with oxygen. This can be given or this can be given. So NO2 has got two different atoms through which it can ligate. But it ligates through only one atom at a time. Such kind of ligands are called ambidentate ligand. Ambidentate ligands are unidentate ligands or monodentate ligands, but they have got two donor atoms, two different donor atoms. So NO2 is that kind. Either through N it can be given or through O it can be given. Whenever N is donating, it is written as NO2. Whenever oxygen is donating, then it is written as ONO. Whenever NO2 is the one, then we write nitrito N as a ligand. Whenever ONO is written, we have to spell nitrito O. Right? This is the way we have to distinguish that. Cobalt 3 ion, cobalt 3 ion. So here there is no counter ion. Counter ion is not there. So you have to find out the oxidation state based on the charge on the complex ion and write the oxidation number in the parenthesis and say at the end ion. Right? So this is the way you can do. Now, tetraamine dichlorido. Okay. So cation is a complex entity and anion also complex entity. Okay. Dichlorido cobalt. Okay. Hexacyno chromium 3. Chromium 3. Okay. Chromate 3. So this is the way that we have to name. So because this carry -3 charge and this carry +3 charge, right? +3 charge, right? Okay, +1 charge into 3, +1 charge. Okay, the cobalt here is +3. This is -1, -1 into 2. Therefore, 3 - 1 is +1. 3 - 1 into 2 is totally +1. So +1, this kind of 3 are there, 3 plus and 3 minus. Okay, so all these are the calculations to be done for naming. Okay, this is tetra aqua dichlorido chromium 3 nitrate. Normally for chromium and cobalt, the oxidation state will be 3. Okay, in only special cases it can be different. Otherwise, chromium, it will be 3. Chromium 3 nitrate. Okay. Now here SCN is there and ammonium ion is there as a cation. Ammonium hexathiocyanato. SCN is thiocyanato. Yes, here also thiocyanato. Yes. So the first letter is the ligating atom. Thiocyanato. Yes. Here also it is ambidentate ligand. It can be thiocyanato N. SCN. Thiocyanato. Yes. Chromate 3. Okay. So this is the way the naming should be done. Okay. Finally, check these answers. So various types of ligands are there. Therefore, I'm taken many examples. So here you have to take many examples and many workout you have to do, and then you have to be perfect in that. So every example, you have to learn something, right? So pentaamine, carbonato, CO3 2-, carbonate ion, carbonato. Anion should be carbonato. Cobalt 3 chloride. Okay, what is this PY? PY is pyridine. Okay, so this is tetra pyridinium, okay, pyridine, tetrapyridine, platinum 2, tetrachlorido platinate, tetrachlorido platinate 2. Platinum has got a 2 oxidation state, either 2 or 4. Okay, we have to check with that, right? Okay, so these are the ways of naming. Please take up the work of practicing, okay, more in length, so that it can be perfect in that. You can be perfect in that, right? Now coming to the another topic, isomerism. What are isomers? What is meant by isomerism? We had been talking about the isomerism in the organic chemistry also. Isomers are those which are having same composition, but their arrangement is different. Arrangement of atoms are different, or bonds may be different, due to which their properties are different. Okay, so isomers are having, in as far as carbon compound is concerned, they are having same molecular formula. Okay, and their properties are different. If the properties are too much different, then they may be functional isomers. All these things we have learned in the class 11th. Now, what about the isomers in coordination compounds? Yes, in coordination compounds also, different types of isomerism is there. Isomerism is possible, right? So, these are the different types of isomers. So, isomers are having same formula, but different properties. Generalized definition. It is a generalized definition. Isomers are those who are having same formula or same composition, but different properties. So broadly, they can be classified as structural isomers or stereoisomers. What is the difference between these two? Structural isomers, these isomers have, within the molecule, there will be different bonds. Bonds are different. Because of the bonds are different, different bonds are there. They are structurally different, therefore structural isomers. But in stereoisomers, their spatial arrangement is different. In three-dimensional space, how they are arranged are different. This leads to stereoisomers. And among structural isomers, there are 4 kinds of isomerism. There are 4 types. One is ionization isomerism, solvate isomerism, linkage isomerism, coordination isomerism. So these are the 4 types of isomerism which is there in the structural isomerism. Structural isomerism has 4 types. In stereoisomerism, there is geometrical and optical isomerism. Okay, so let us look into this, all these things one by one. What is ionization isomerism? 2 compounds. Okay, so 2 compounds. Okay, if it is blurred, I will write here. One is CO, NH3 5 times, SO4. This is one coordination compound, Br, okay, with bromine as a counter ion. So another one is CO, NH3 5 times, Br inside the square bracket, SO4 here. So this is isomer of this. There are the 2 compounds that I have written. They have the same composition. Both have cobalt, both have ammonia 5 number of ligands of ammonia are there. One sulfate is present and one bromine is present. But the difference is sulfate is a ligand here, bromine is a counter ion, but this is get exchanged. So if it is so, then what is going to affect is, if bromine is outside, this is ionizable, sulfate is not ionizable. This here, sulfate is ionizable, but not the Br. Okay, so these are all chemically can be proved also, chemically tested. If sulfate ion is outside, if you add barium chloride, it will answer. Barium chloride, it will give the white precipitate of barium sulfate, because sulfate ion is free. That is a counter ion. But if you test the presence of bromide ion, it won't give the test. But similarly, if this bromide ion can be tested, but not the sulfate ion. If you add barium chloride, it won't answer, but it may answer AgNO3 test. Silver nitrate will give silver bromide. Okay. Therefore, these are having same composition, but they do ionize different way. They ionize in a different way. Therefore, they are ionization isomers. Right. Okay. So you can write many number of examples of ionization isomers. Now, another one is linkage isomers. Linkage isomers are due to the ambidentate ligands. Ambidentate ligands, as I told you, the same ligand composition is same. Okay. Okay. It is not giving. Okay. What I wanted to tell you is, if it is NO2 and ONO, the composition is same, but the ligating atom is different. That's why it is a structural isomers, because central atom binds with nitrogen here. The bond is metal atom and nitrogen, but in this case of metal atom and oxygen, so bonds are different. Therefore, it is a structural isomer. So, linkage isomer from the some complex ion structure, but the point of attachment of at least one of the ligands differ. One of the ligands differ. NO2 and ONO, if it is present here, these are the structural, these are the linkage isomers. Okay. So among structural isomers, there is ionization isomers or linkage isomer. Both have different bonds. Both have different kind of bonds. Okay. So in the previous case, bromine may be having attached to the central atom, or it may be attached to the total ion itself. Okay, ionic bonding it may do. Right. So this is the linkage isomer. Here is an isomer. NO2. N is there here. O is there here. NO2. Ligating atom is different. Okay. So this bond is different. This bond, metal atom and oxygen. Here metal atom and nitrogen. Therefore, these are different isomers. And because of their colors also different, they are having different properties. Their colors are different. Okay. Now, thirdly, this solvate isomers. Solvate isomerism is due to the ligands. The ligands can be the solvent, or solvent can act as a ligand. Okay. A solvent, water, can act as a ligand also. Therefore, it is arises due to that fact. Okay. Now, chromium Cr H2O 6, H2O6, 3 plus. Okay, or Cl3. So isomer of this one is Cr H2O6 Cl heterolytic and Cl2. Okay, H2O5 dot H2O. Okay. That means one of the water molecule is hydrated form. It is not acting as a ligand. Right? So the coordination number is 6, and here also 5 plus 1, 6 only. Chromium is having coordination number 6. But instead of 2 counter ions, it is 2 counter ions are here and 3 counter ions are there. Chloride ions. So number of solvate molecules acting as ligands are different. Then this leads to solvate isomerism, right? Or hydrate isomerism. Hydrate isomerism in case of ligand is water, or any other one, solvate isomerism. Now, coordination isomerism. Fourth one is coordination isomerism. In coordination isomerism, first condition is both should be, cation and anion should be a complex ions. Both cation and anion is complex ion, then only it can. So there are 2 metallic species, cobalt and chromium. This cobalt is having 6 ammonia and chromium is having 6 cyanide ions. The ligands are different. Chromium binds with 6 cyanide ligands. But its isomer is chromium can bind with 6 ammonium ions and cobalt can bind with 6 cyanide ion. They interchange. Suppose if they are interchanged, then the composition is same, but the complex ions are different. Therefore, it is a coordination isomer. Now recall, what type of isomers are these?
Linkage isomer.
So you can identify easily. This is linkage isomer. Okay. So I remind you this linkage isomer. Its color and ONO and NO2, right? Yellow and orange, different colored. Linkage isomers, right? Okay. Are these same type of isomers? Are they linkage isomers? Yes, it is also true. Ambidentate ligands are there. SCN and NCS. Okay, that's the point to see. Okay, again, these are also different colored. Give evidences that CONH35ClSO4 and CONH35SO4Cl are ionization isomers. What is the evidence that you can give? You can give the test of sulfate ion or test of chloride ion. This will answer for AgNO3 because Cl is as present as a counter ion. This will answer for barium chloride. Okay, barium chloride test, it will give barium chloride test. Okay, that is what we have to say in sentence. What kind of isomerism exists between CrH2O6Cl3 violet color, CrH2O5Cl2H2O grayish green?
Solvate isomerism.
CH2O is here, number of H2O as a ligands is different. It is solvate isomerism. So, 4 isomerism: ionization isomerism, linkage isomerism, solvate isomerism, and coordination isomerism. These four are structural isomers, right? Structural isomers. Okay, 4 isomers that we have seen, they are all structural isomers. Now come to the stereoisomers. Let us know about stereoisomers. Geometric isomers, cis and trans isomerism. Geometric isomers are cis and trans isomers. Okay, what way? How they are arranged? Okay, in organic chemistry, we had that cis and trans isomers, right? And in coordination compound, how it is present, let us see. And optical isomers. Optical isomers means their spatial arrangement is different, due to which they can rotate the plane polarized light towards the right or towards left. Again, non-superimposable mirror images that they can do. And if a complex can have the geometry such a way that the one which is the mirror image of the other and one is optically active, then another one is also, the mirror image also will be optically active. One is dextrorotatory, means another, its mirror image will be levorotatory. Okay, let us find some examples of all this, right? Okay, geometric cis and trans isomer. If 2 identical occupy adjacent position, then we call it as cis. 2 identical ones are at the adjacent position. If they are opposite, then it is trans. Okay, this rule holds good for all tetrahedral, not tetrahedral, square planar and octahedral complexes, right? All complexes. So optical isomerism arises due to non-superimposable mirror images. Non-superimposable mirror images. So any compound, not only carbon compound, any compound can be optically active if it possesses no plane of symmetry, no line of symmetry, no point of symmetry. Okay, symmetrical things are not present in a compound, then it will be optically active. Now, let us see the geometrical isomerism, right? Geometrical isomerism, atoms or groups are arranged differently spatially relative to the metal ion. Now, take the examples of PTNH2, NH3 twice Cl2. PTNH3 twice Cl2. Platinum is the central atom. It is a square planar complex. Okay, square planar complex. And 2 NH3 are here, right? Nitrogen is giving a pair of electron, right? Now 2 chloride ions. Okay, Cl2, there are 2 Cl, right? Okay. Okay, this is one way of arrangement. Another way of arrangement in the space is central atom. One NH3 is here, another NH3 is here, opposite to this. One Cl is here, giving a pair of electron, another Cl is here. Okay, so this is present at one side, chloride one side. Okay, so this is cis form. This is cis form, and this is trans form. This is trans form of that. So cisplatin, this is a cisplatin. I think you might have heard. Cisplatin is the one it is used against cancer. Okay, it is a medicine, right? Cisplatin, and cis form is acting as a medicine, but not the trans form, right? So therefore, the geometrical isomers are also important. So this is geometrical isomers arise due to the spatial arrangement is different. All bonds are same. Remember, platinum, ammonia, two bonds are there. Same bond is there. Okay. So if it is bonds are different, then it will be a structural isomers. But here bond is same. But NH3 is opposite, diagonally present here. That is transform. Right. Okay. Now you can able to see here. PT NH3 twice Cl2. Cl here, NH3 here. This is a transform. For the octahedral complex like CO NH3 4 Cl2. CO NH3 4 all are at one side and Cl2 at another side. This is cis form. Okay, oppositely it is there. Cl is opposite. This is opposite. This is opposite. Okay, oppositely they are present. Then this is the transform. This is the transform. Similar kind of ligands, if they are present oppositely, then it is a transform. Okay. Now, what are the types possible? What are the types possible? Suppose I will judge the general form of this. Okay, Ma2B2. We have seen that among the square planar complexes, if there is for the metal atom, there are A type of ligands 2, B type of ligands 2, then it will form square planar complexes of this type will have cis and transform. Just I have taken an example: platinum, NH3 twice, Cl2 twice. NH3 is A type and Cl is B type. So Ma2B2 type form square planar complexes form the cis and trans isomer. Suppose if it is Ma2BC, instead of B, there are two again different ligands. Will it form cis and trans isomer? The answer is yes, because if the metal is here, okay, A2BC, metal is here, A2BC. Look at this. Similar atoms are at one side. Similar atoms are opposite. Therefore, it is trans. Okay, it can be applied to this also. Need not be both ligands should be same. It need not be so. This is not the rule. Therefore, Ma2BC are also possible. Okay. Then MAB2. MAB2. AB2 means unsymmetrical didentate ligand. Unsymmetrical didentate ligand can have this kind of thing. So okay, M is there. Okay, AB is a didentate ligand. So this is represented like this. One is A, another is B, and AB is having bond or structure. So it's commonly written like this. MAB is one ligand, didentate ligand, and MAB, another didentate ligand. Okay, A also donates a pair of electron, B also donates a pair of electron, right? Okay, so this is okay. This is oppositely they are there, right? Oppositely they are there. A opposite to that, B is there. A opposite to that, B is there. Okay, I will draw another one. You can identify which is cis form and another is AB is here and BA. BA. Okay. So AA is opposite. BB is opposite. This is transform. Okay. This is transform. AB is opposite. AB is opposite. Okay. We'll do. Same kind of atom should come oppositely. Then it is a transform. Therefore, this is also possible. In square planar complexes, all these are the types form. These types form geometrical isomers, cis and transform. Okay. So various examples of ligands that you can take once it is taken in general format, right? Okay. Now this M, okay, AA2, B2. If this is the complex, MAA2, B2. So what is the coordination number of this particular complex? The coordination number is not 4. Coordination number is not 4. Remember, a didentate ligand, 2 ligating atoms. Therefore, 2 ligating atoms one gives a pair of electron. Therefore, it is 4A plus 2, 6. If it is written like this, it is like CH2NH2, CH2NH2. Okay, this is one molecule. 2 electrons it is giving. Such kind of 2, AA2 means this is symmetrical didentate ligand, 2 are there. So totally 1 plus 2 pairs. Such kind of 2 means 4 pairs. So coordination number is number of coordination bond that metal does. Therefore, it is 4 plus 2, 6. This is forming octahedral complex. This is forming octahedral complex and the metal is here. Say metal is here. AA. So you can take AA here. This is one AA. And octahedral complexes are written here like this. Okay. Now, AA, you write here AA. And this is B and this is B. This is one form. This is one of the forms. Okay. I will draw here. Metal here. Then AA. Then AA here. And B here. Now, which out of these two is cis form and another is transform? You can identify. Okay, all A's are at one side and B's are at the other side. Therefore, this is cis. Okay, AA is opposite. Therefore, this is trans. Okay, so this way you can identify the kind of geometrical isomers that can be written over this. Okay. Now, and out of these two, this cis form is showing optical isomerism. Cis form of MAA2B2 will give optical isomerism. That means it has got its non-superimposable mirror images. But this has got line of symmetry. Among this line, the symmetrical. Therefore, transform is not optically active. Transform is not optically active, but cis form is optically active. So there are few optically active. Okay, 1 minute. Or few optically active compounds are there. Optically active compounds are of the type this B2 or MAA3. These are the two types which show optical isomerism. Okay, square planar complexes will give Ma2B2 cisplatin type, Ma2B2, or Ma2BC. Taken the example of this, MAB2 unsymmetrical tight-end ligand, and MABCD type also. So these are the types of square planar complexes that is possible. And optical isomers, MAA2B2, MAA3. Okay. So if you note down all these things, okay, the confusion will be less. So generalized format you write so that it becomes easy. Optical isomerism, okay. Stereoisomerism, isomers have opposite effect on plane polarized light. Okay, this is the picture that you have seen. A vibrating light in all direction passes through the polarizing filter. It becomes unidirectional. Polarized light passed through a tube containing a sample. This is tilted. This angle it is tilted. If the angle is towards right side, it is dextrorotatory, or it is levorotatory, right? Okay. So exhibited by the molecules that have non-superimposable mirror images. So the enantiomers, isomers of non-superimposable mirror images. Okay. Suppose I told you this MAA2B2 or MAA2BC. So if this is M, okay, I have to take cis form of this. This is the cis form. This is the cis form of this. MAA2B2. All A at one side and B another side. It has got its mirror image. It has got its mirror image, right? Okay. So this will be AA here. Okay. B and B and A and A. Okay. So metal is here. Now by just looking at it, we can't predict that these two are different. We may think that both are same, but they are like left hand and right hand. They are non-superimposable. This need models. Okay, models constructed for that, and you can say that. Sorry, I'm not having videos for this, but these show optical isomerism. Whatever it is, if you see the video also, practicing is needed. Such kind of structure is needed, and imagination you should develop. Okay, then only you can able to do well in that. Right. So if it is the dextrorotatory, this will be levorotatory. Okay, like this. Like this mirror images, you can see here. This is of the type MAA3 type. Oxalate ion or ethane 1,2-diamine. Oxalate or ethane 1,2-diamine. Cobalt 3-ene or 3-enes. Here example taken is this 3+. Okay. Okay, this is showing optical isomerism. It has got a mirror image, non-superimposable mirror image. Okay, so in the biomolecules or also we will find such kind of isomerism, and you can rotate and see that they are different. So you make such kind of ball and stick model and rotate it and see that they are not superimposable. They are not matching, right? Okay, concept check. Does COEN twice Cl2Cl exhibit geometrical isomerism? Questions may be asked like this. COEN twice Cl2. Okay, what you have to do? You have to compare with M. En means it is AA twice B2. It is of this type. Does it exhibit geometrical isomerism? Does it exhibit geometrical isomerism? Yes. Cis and trans isomer I have shown you, right? cis and trans isomerism. Ene is symmetrical didentate ligand, and cis form of this is optically active, right? Cis and trans isomers are there. As trans isomer has got a plane line of symmetry, therefore this is geometrical isomer. Yes is the answer. Does it exhibit optical isomers? Optical isomerism? For that, answer is transform no, cis form yes. Cis form of this type forms this. So it's important thing to be remembered. Indicate the complex ion which shows the geometrical isomerism. Indicate the complex ion which shows geometrical isomerism. Okay, these are all the charges. Okay, these are all the charges. Okay, this here, this is of the type MA4B2. Okay, MA4B2, this type. Compare that. MA3, MA3B. Here it is MA6. Here it is of the type MA5B. MA6, we can say that no, because all are A and replacing one by the other will not be another one at all, right? Another kind of arrangement cannot be. So wherever 6 coordination number is there, octahedral complex, 4 are there, then it is square planar complex. Even MA3B also not possible. MA4B2, we have checked that A4B2, okay, is the one which has geometrical isomerism. One which has geometrical isomerism. Now, the stabilization of coordination compound due to chelation is called chelate effect. Chelation, I talked about chelation. Which of the following is the most stable complex species? Which of the following is most stable complex species among this?
Option 3.
Carbonyl, it is a monodentate ligand. CN is a monodentate ligand. H2O is a monodentate ligand, but oxalate is a didentate ligand. Therefore, it should form more than one pair. Then it is ring-like structure. Then chelating effect will be there. Therefore, 3 is the answer. Okay, which of the following complexes heteroleptic? More than one options are correct. Which of them are heteroleptic? Suppose if there are 2 types of ligands, then it is heteroleptic. Therefore, this is a heteroleptic because NH3 and Cl2 both are in the square bracket entity. And here also that it is heteroleptic complex. If 2 types of ligands are there along with a metal atom or ion, then it is a heteroleptic complex. Identify the optically active compounds from the following. Optically active compounds. Okay, this is the way the questions are asked, right? MAA3 type. Okay, 3 plus is the charge. Okay, 3 plus is the charge here. So this shows optical isomerism. Therefore, I told you 2 types which will form the optical isomerism is MAA2 type, MAA2, MAA 3 types, 3 times. This type and MAA2B2 or MAA2BC. Cis form of this will show. Okay, cis form of this will show. Okay, right. So NH3 and Cl will not be because only one Cl is there. Wherever it is taken also, it will be same. Okay, write the types of coordination compound given below, show geometrical isomerism, write the structure. Okay, so this is as a homework that you can do. What are the structures of that you have to practice? Taking that you have to practice and imagine, right? So that's what the homework needed. Now let us come to the different theories of coordination compounds. Different theories. There are 3 theories. One is Alfred Werner's theory, and valence bond theory and crystal field theory. These are the 3 theories which explains about how the bonding in the coordination compounds is. Alfred Werner, who was a professor, full-time professor at a very young age, 29 years. He was a professor and did extensive work on the coordination compounds. When the people were not knowing anything about coordination compounds, he started doing work on that. Okay. And he got a Nobel Prize in 1913 for that. Okay, it's interesting to know his life history. Okay, his hard work. Okay, and given him the Nobel Prize. Right. What he did was he took the samples of coordination compounds. They differ in their property, but they are having composition like this: COCl3 6NH3, COCl3 5NH3, COCl3 4NH3, COCl3 3NH3, 4 compounds. Okay, he is surprised to see that there are, from the conductivity experiment, he saw that total number of ions present in this molecule is 4. But total number of ions present here was 3. For this it was 2 and there was no ions at all. Okay, ions at all here, 0. Then he has tested the free chloride ions through the silver nitrate test. This was giving 3 moles of AgCl, telling you that this was giving 2Cl minus ion. Okay, and that there are 3 chloride ions which are ionizable in the, and they is called as coordination entity. Your internet connection is unstable. Okay, fine. And 5NH3 and 1 Cl is inside, therefore only 2 Cl2 are there, therefore free Cl2 is 2, and therefore he could able to give the structure of this. And when it is only 1, it is like this, and no chloride ion, therefore it won't give any AgNO3 test, or the moles of AgNO3 we didn't get, and the conducting ions are also 0 because it was neutral. 0 charge on the complex ion. So because of these things, he could he told that every metal atom or ion, every metal atom has to satisfy 2 valencies. One is primary valency and the secondary valency. Primary valency is due to counter ions. For example, copper chloride. Copper has got 2 plus charge, right? So that means it has to give 2 electrons. That is a primary valency. And every metal atom has secondary valency also. Secondary valency is it can attract some fixed number of ligands. Cobalt, coordination number is 6, means it always attracts 6 pairs of electrons. Always it binds the 6 ligands, mixed monodentate ligands, or it accommodates 6 pairs of electrons from the ligands. So this particular establishment of the theory, he got the Nobel Prize for that, right? Now the second theory is the valence bond theory. Valence bond theory assumes that the metal atom or the ion should possess some empty orbitals, and that is empty orbitals they should possess, the number of empty orbitals must be equal to number of approaching ligands. If 6 ligands are approaching the metal atom, there must be 6 orbitals which are free to accommodate. Now suppose if it is not if the orbitals are not fully free, then electrons in the d orbital, they may get shifted or they may get paired up in order to accommodate the ligand. This happens when the ligand is very strong. If the ligand approaching is strong, then pairing of electrons may take place in the d orbital, right? And the orbitals undergo hybridization. What kind of hybridization? Depends upon the number of orbitals required to accommodate the approaching ligands. If 4 ligands are approaching, their possible hybridization is either sp3 or dsp2. If sp3 is the hybridization, Then tetrahedral is a geometry associated with the coordination polyhedra. If it is dsp2, then it is square planar. If it is d2sp3 or sp3d2, then it is octahedral. Okay, so let us take the examples and find out about it. Now I am talking about this Cr, chromium, NH36. Okay, NH36 3 plus. How this formation of this particular coordination compound takes place? Okay, Cr, NH36 octahedral complex. Now you know that chromium, an atom is having electronic configuration of 3d 5 electrons, argon core with 5 electrons, 3d 5, 4s1, right? This is the electronic configuration. Here chromium is present in Cr3 plus, in the Cr3 plus oxidation state in this complex, because NH3 is a neutral ligand and the charge of 3 plus is the charge on chromium, right? So 3 plus means it has to lose 3 electrons, primary valency, it has gone to the counter ion or so. So only 3 electrons are remaining like this. Then the available orbitals are 1, 2, 3, 4, 5, 6 orbitals are available. If there are 6 number of NH3s approaching, is undergo hybridization. What is the hybridization? D2sp3. D2sp3 is the hybridization. Okay. So when it is hybridized, hybridization means the orbitals, intermixing of orbitals to give orbitals of equal energy. All these 6 orbitals are having same energy and they are accommodating 6 pairs of electron donated by each ligand. Each ligand donate 1 pair of electrons, so that total 6 ligands donate 6 pairs, and therefore this is how the electronic configuration is present, or the complex is having this kind of configuration. So what is the plus point of this theory is, it tells about the hybridization concept and thereby it tells about the geometry of the polyhedra authentically. And the presence of unpaired electrons here, we can able to calculate the magnetic momentum associated with it, mu, or we can say whether it is paramagnetic or diamagnetic. So it is advanced theory. So advanced than Alfred Werner's theory, right? So let us see some more formation. Nickel cyanide, NiCN4, 2 minus. If this is the complex. So nickel, the electronic configuration you must able to write, right? And the configuration you should able to know. Nickel, this will not be given. Okay, nickel is having argon core, okay, and 3D 4s, okay, 4s2. For knowing the 3D configuration of nickel, you have to say the in sequence, say the 3D series in sequence. Okay, scandium, titanium, vanadium, chromium, manganese, cobalt, nickel. So this is 3D7 4s2. Okay, so scandium is 1, 3D1. Okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. Okay, this is 8, 3D8 4s2. Here nickel is in the form of Ni2 plus. It is in Ni2 plus. That means 2 electrons have gone. Ni2 plus means outermost electrons have gone. So it has got 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right. Now, as I told you, depending upon the approaching ligand, the electrons can be get paired up. This is what happened here. So if this electron gets paired up here, one more orbital is made empty. This happens because cyanide is considered to be the strong ligand. Cyanide is a strong ligand. Therefore, pairing up takes place. Therefore, the kind of hybridization occurs is dsp2, and 4 orbitals dsp2 accommodate 4 cyanide ions. When the hybridization is dsp2, it is square planar. Okay, so this kind of accommodation is possible, this kind of shifting is possible, therefore it is so. Okay, suppose if you want the geometry of this NiCl4 2 minus, absolutely same kind, NiCN4 2 minus, NiCl4 2 minus, chloride ligand. Chloride ligand is considered to be weak ligand. Okay, so I'll tell you CnNH3. Okay, CnNH3, strong ligands. Chloride ion or bromide ion, these are weak ligands. Okay, only on that questions will be asked. There are many lists are there. I'm going to tell you, but these are the main thing which will be asked in this theory, right? So if it is NiCl4, this pairing up doesn't take place. Therefore, the hybridization is sp3. So NiCl4 is sp3, whereas NiCN4 is dsp2. This is a square planar complex. This is tetrahedral complex. Okay, so this theory is more authentically saying about the geometry. Okay, because of the available orbitals and based on the nature of ligands, right? So here again, zinc hydroxide, ZnOH 4 times. Okay, this is the complex 2 plus or 2 minus because OH is minus. Zinc 2 plus oxidation state, zinc, the oxidation state of zinc is 2 plus, therefore 3d10. Okay, 4s is empty. 4s, therefore it has to undergo. There is no option for pairing up. Already electrons are there, therefore there cannot be any pairing up possible here. So sp3 is the hybridization. Therefore, it is a tetrahedral complex. You can see the tetrahedral 1, 2, 3, 4. Okay, this is tetrahedral, right? Geometry. Okay, so another one is crystal field theory. In crystal field theory, okay, so we assume that the ligands are point charges. Ligands are point charges, and the metal ligand bonding is entirely ionic in nature. Okay, so there are strong field ligands and the weak field ligands. By the approach of ligands, say suppose the ligands are approaching, the electrons distribution on the atom changes. They are affected. Okay, so these electrons which are present in different orbitals, they get affected. So there are 5 orbitals, degenerate orbitals, 5 kinds of orientation along the planes in the d orbital. One is dx square minus y square, dz square, and these are all on the axis. You can see these are the axis, and on that axis the electron movement is there, and this is along the z axis. Here dxy, so it is in between the axis. If this is the axis, x-axis is y-axis, orbital is here. In between the axis, xy plane, dxz plane, okay, and dyz plane. This is y, this is z, means it is in between. Okay, so here is one set. These 3 orbitals are in between the axis, the planes in between the axis, but these are on the axis itself. This has something to do with the disturbance caused by the approach of ligands. Now, if the ligand is approaching, then there is a total disturbance. 6 ligands are approaching, they have to approach through axis only. 6 ligands through axis only. So those which are along the axis, electrons along the axis, they are disturbed more than those which are in between the axis. They are little safe. Now, due to which dz square and dx square minus square, they are more disturbed, will be having more energy, and this is called EG set. And dxy, dyz and dxz, there is these 3 orbitals, less energy, but average energy is almost more than what energy they possess before approaching of ligands. After approaching of ligand, energy increases. But among these two sets, the distribution is like this. Okay, this is called crystal field splitting. Suppose there are 4 electrons. 4 electrons. That means chromium 2 plus is having 4 electrons. Chromium 2 plus is having D4 configuration, 4 electrons in the d orbitals. So T2G set there will be 3 electrons, and EG there will be 1 electron. Why this is the distribution? Because H2O is a weak ligand. H2O is a weak ligand means they cause this gap less. When the gap is less, electrons can jump easily. So the 4th electron will be here, and the configuration is written like this: T2G3 EG1. This is the configuration in the orbitals, right? Suppose if the approaching ligand is Cn, as I told you, Cn is a strong ligand. This causes much difference. This difference is delta octahedral crystal field stabilization energy. Now the 3 electrons after the 4th electron, it may not jump to this level, therefore it will remain there. So if the approaching ligand is strong, then T2G4 EZ0 is a configuration. So electron distribution in degenerate orbitals, okay, before they are degenerate, after that their degeneracy is lost, and the distribution about the configuration is to be written. Right? If the ligand is weak, then more number of unpaired electrons will be there. Therefore, it is a high spin complex. So magnetic property will be paramagnetic, and also it is a high spin complex. Spin will be more. If the approaching ligand is more, this gap is more, therefore pairing up takes place. Therefore, this is a low spin complex. So the speciality of this one is that will distinguish about the magnetic properties of the complexes associated with it. Okay. Okay. So I told you that the jumping of this, if it is there, it needs energy. And okay, this artist wheel has come little earlier. Okay. Right. Okay, I will talk about this and then go for that. Okay, if this is a complex ion, this is the complex. Okay. And if there is 1 electron, say D1 configuration, okay, the compound is here, kept here, and the VIB-Guyot, the 7 colors of the light is being passed through, so that this electron gets excited by absorbing these 2 colors. By absorbing these 2 colors or these 2 wavelengths, that energy is enough to make that to go to the EG level, and other colors are left as it is. This is transmitted colors. This is absorbed colors. Okay. So the incoming colors, among the incoming colors, only few are taken, absorbed, and one which is given out is what that we are going to say. So I was talking about the artist wheel. That is the thing. If orange color, this is absorbed, this is what we are going to see. This is what the color of the complex that we are going to see. If this is absorbed, this is what the color that we are going to see about the complex. Okay. So this is the way that we can able to compare. Okay. So hence, so not only the ligands, approaching ligands, if the oxidation state of the metal is changes also, the color may change. Oxidation state of the metal changes also, the color may change. Okay. So these are the different things that we'll understand from the crystal field theory. So we can arrange all the ligands in the increasing order of their field strength. Okay. So this field strength, carbonyl is highest among them. Therefore, you can take these are strong ligands and these are weak ligands. H2O is mediocre, and whenever these are approaching, consider that these are very strong ligands, right? Okay. So successfully it explains the color formation of the complexes, right? And therefore, the successfulness of this theory is it can able to tell about the high spin complex and low spin complexes and color of the compounds more efficiently. Therefore, it is more advanced theory. Okay, these are the important concepts in this chapter, and keep solving many of the question papers, sample papers especially, of the when many are available nowadays. Get this solved. You will get the ideas what is important in each chapter, and also you will get what is in examiner's mind. That is very important to study. So once the syllabus is over, solving the sample papers is a best practice. Okay, and keep discussing with the teachers so that you can end up with a good score, definitely. Okay, all the best for all of you. Thank you. The chemistry sessions are going to end now, and the biology classes may start in the next days to come. Thank you, one and all.
Thank you, sir. Thank you, sir, from all the students from Bangalore Urban.
Thank you, sir.
Thank you, sir.